Alright, so we are back at it. I hope your travel to your location, wherever that may be, was smooth and that you all are doing well. Everything is good here in Lubbock. We're ready to proceed on with our first lecture here after break. And the topic of this video is going to be on titrating a weak acid with a strong base. Now, before break, we worked the example of a strong acid with a strong base. Now we're going to follow up with the weak acid-based titration. It's really important that when you're starting a problem, you understand if you're titrating a strong acid with a strong base or a weak acid with a strong base or a weak base with a strong acid, because you got to consider different things for each type of problem. The problem's worked a little bit differently for each case. So you have to ask that question first. Now for this case, as is really every case, the titration curve is going to have a few different regions. And we want to identify and understand those regions, and then we're going to learn what controls the pH in each region, and that's going to be crucial. So the first region of any of the titration curves is the initial pH before any of the titrant has been added. So in this particular case, if we're titrating a weak acid, the weak acid is our sample, and the initial pH is just going to be the pH of that solution. There's no titrant added, so we only have the weak acid in the aqueous solution. And however good the weak acid is at donating protons is going to determine the pH. We just need to work the equilibrium rise table, treat it like a weak acid equilibrium problem, like from the previous chapter. We'll see that in a couple minutes when we work an example. The second region of our curve is after some titrant has been added, but we're not yet to the equivalence point. In this region, region B, it's called the buffering region because the solution essentially becomes a buffer. We start to titrate the weak acid, and we convert some of the acid form into its conjugate base. So we end up with a mixture of both of these, the HA with the proton and the A minus, the conjugate base. And of course, if we have both of these in solution at the same time, we've got ourselves a buffer. So because of that, we can use the HH equation. If we find the concentrations of the acid in the base form, plug it in and solve. An interesting point within this region B is at the half neutralization point. Other people might call this half the equivalence volume. 1/2 VEQ, where VEQ is the volume of the titrant required to reach the equivalence point. Now if you're at the halfway point of the titration, a really interesting thing happens. At the halfway point, and only the halfway point, the concentration of both of these become equivalent, and because of that, the Henderson Hasselbach equation reduces to the pH is equal to pKa. So at the half equivalence point, this is true. So it's sort of an interesting point along the curve. But we'll see that when we work the example, I think, here in a few minutes. But there are a few other points along the curve that we should talk about before we begin a sample problem as well. What if you keep titrating and you get to the equivalence point? Well, at the equivalence point, all of the acid has been converted into the base. Here we call that the A minus form in this example, because HA is with the proton, the A minus is the base, the conjugate base. At that point, all of the acid was converted to the base. So if we solve for the A minus form concentration, we could write the key reaction for the hydrolysis of that weak base with water to make HA and OH minus. So we could see that because we make OH minus, we'd expect the pH to go up some. So this reaction is actually crucial at the equivalence point for a weak acid with strong base. This hydrolysis reaction predicts that the pH should be a little bit basic, and in fact it will be for this type of titration. The last region is D, beyond the equivalence point. If you keep adding titrant, which is going to be a strong base in this case, you're just going to load the solution with OH minus. You're going to increase its concentration. And if you can solve for the molarity of the stuff that's in excess, you're in business, because you can get POH, and then you can get pH, and that would be our strategy there. So we're going to work through an example type of problem here to help us learn how to handle this condition, okay? I want to present that to you now, and then we're going to work our way through it. So here's the sample problem. In this problem, we're going to titrate a sample of HNO2. Now this is not HNO3, this is HNO2, which is a weak acid. This particular acid has a pKa of 3.34. Now if I want to solve for the Ka, I can. I take the anti-log operation, essentially take 10 and raise it to the negative 3.34, which yields a Ka of 4.57 times 10 to the minus 4. So indeed, this is a weak acid, right? And what I'm going to do is I'm going to take that HNO2 sample and I'm going to titrate it. I'm going to set up my burette, my long glass tube, and I'm going to wash that burette and fill it up with 0.2 molar KOH. And this is aqueous KOH. It's an aqueous solution of potassium hydroxide. Of course, this is a strong base. It's a group 1 metal hydroxide solution, right? So we're titrating a weak acid with a strong base. This is the class or category of titration that we're talking about here. Now along the curve, we'd like to compute the pH at several different points. The first point will be determining the pH before any titrant is added. So basically, if I put a pH probe inside that solution, what would the pH meter read before any of my strong base is added? Okay. Well, let's think about how to handle that situation. Well, a few seconds ago, I just kind of outlined our approach. And we said that the initial pH is that of the weak acid solution. No titrant's been added, so we can calculate like a weak acid equilibrium problem, like we learned how to do in the previous chapter. And this is certainly true, because if we haven't added any titrant yet, all I've got is a beaker full of a weak acid of 0.1 molar. So can I just work my rice table and figure out what my pH should be? Sure, I can do that. But before I do that, I got to figure out what my reaction is of consequence. So here we've got our acid, the HNO2, and it can act as an acid, donating a proton, H+, and make the NO2 minus anion. So that's my R. That's my reaction. I can specify my initial conditions. Now in the problem, if I look back, I had 0.1 molar HNO2, 40 milliliters of it, right? So notice in my rice table, I add 0.1 molar, 0 and 0. Now certainly this acid will donate some of its protons. So we're going to shift to the right. I'm going to make X and make X. Oops, that's the third column. I'm going to make X and make X, using up X quantity of this stuff. And then at equilibrium, I'll have 0.1 minus X, X, and X. Of course, now we're going to do our usual thing. We're going to go to our Ka expression. Products divided by reactants. So I have X times X, or X squared, divided by 0.1 minus X. And that's going to equal my Ka, my equilibrium constant for this acid, which on the previous slide I also decided was 4.57 times 10 to the minus 4th. So now I just need to solve for X. If I was working this one, I'd be a little concerned about doing the assumption that X is small. Reason being is that this Ka is fairly sizable, and if you compare this number with this number, yes, this is a lot smaller, but it's starting to push the limit a little bit of whether the assumption is going to work. So I'd probably just work it out and use the quadratic if I was doing this, just to be safe, okay? And in doing that, then I would write X squared, and I'd take this denominator and I multiply both sides by this. So then on the right, you have to multiply the 4.57 times 10 to the minus 4 times this. So you'd end up getting 4.57 times 10 to the minus 5 when you multiply this number times the 0.1. That would yield that, right? And then you'd have minus 4.57 times 10 to the minus 4x as well. So you just work on the math, right? You clear the fraction by multiplying by both sides. Now you have to get it in the form where we can substitute into the quadratic. So what I'm going to do is take what's over here on the right side of my equal sign and move it back left, leaving my x squared over there. So I leave my x squared there, and I write x squared, and then I'm going to write my term in x. So I'm going to move this one over to the left, and I write plus 4.57 times 10 to the minus 4x. And then I also need to move this over to the left by subtracting from both sides. So minus 4.57 times 10 to the minus 5, and all that equals 0. And this, of course, is a crucial step for us. because this equation, something x squared plus something x plus or minus something, is the form of the equation that we can use our quadratic equation on. And that's what we're going to do. So we go to our equations card and we write down the form of the quadratic equation. As you can see here on the bottom of the slide, it's negative b plus or minus the square root of b squared minus 4ac divided by 2a. And the a's and b's and c's, of course, where does that come from? Well, a is the number which is associated with the x squareds. Right here, that's just 1. B is the number that's associated with x, including the sign, so it's a positive 4.57 times 10 to the minus 4th. And c is this number, including the sign. So what we do is we take that number, the 1, this number, and this number, we just plug it in where we see a, b, and c down here, and we solve for our x. And of course, because the quadratic equation gives us two roots or two answers, the positive root and the negative root, and of course you can see that right here, because you see plus or minus, right? You would solve once using the plus sign, and that would give you one answer. You would then solve this equation the second time using only the minus sign, and that would give you a second answer, okay? Now if you do that for this equation, the two answers which satisfy the equation are negative 0.00699 and positive 0.006535, okay? Now remember, you can't have two answers that describe the same chemical system, the reality of the same chemical system, so one of these must be wrong. And generally, whenever you get a negative number, that's not correct. We can't have negative concentrations of anything, right? It just doesn't physically make sense, okay? So I know right off the bat that that negative response is incorrect, and I can just ignore that one. While it satisfies the mathematical equation, it doesn't satisfy the chemical equation in chemistry, so I can just ignore that. But once I use my quadratic to solve for x, and I find that it's equal to 0.006535, boy, now I'm in business. Because if I look back at my Rice table, I can see that that molarity, x, corresponds to my NO2 minus, but it also corresponds to what? My H plus. So to finish this particular step, I know that negative log of my H plus is my pH. I've learned that a couple weeks ago now. So if I take the negative log of 0.006535, I've got my pH, and that's what I'm going to do. So I break out my trusty calculator, I do negative log 0.006535. I hit my enter, 2.18 is my pH. So it's pretty acidic. So before any of my titrant has been added, my pH was 2.18. Okay. Now that's my answer. But more importantly, what I want you to take from this demonstration is how we got to the answer. Before any of our titrant was added, none of this was added from the burette, was it? The only thing that was important that I had this beaker of a weak acid at 0.1 molar concentration. It has some ability to donate protons in accordance with its Ka, and you just work the equilibrium Rice table. You figure out how many protons you get or what their concentration are and solve for pH, and you're done. It's that easy. It's just like we did in the previous chapter, chapter 18 I guess it was. Okay? It's that type of problem. It's the same exact thing. We haven't even started the titration yet. But now that we can do that one, let's move on to B. Problem B is a little bit different. Because in problem B, now we've actually started the titration, haven't we? We've begun it. Because look, we want to determine the pH after what? 5 milliliters of our titrant has been drained. So in B, we're going to add 5 ml of titrant down into this sample. And we want to know what in the world is the pH after that happens, okay? Well, we just have to think about what in the world is occurring here and maybe make sense of it. And I like to do that here for this problem through an RICF table. we've got a weak acid. We're going to react it with the strong base. And when it reacts, we'll make water. And we're also going to make NO2 minus 1, which is the conjugate base of this weak acid. So what we want to do in this problem is figure out where we're at after 5 milliliters of our KOH, our titrant, has been added. And we could easily do that by making an inventory of everything that's present. Now, to help us do that, we're going to use the RICF table. But since this is a one-way street in terms of a reaction, I'm going to work my table in terms of number of moles of everything. So the first thing I'd like to figure out here is how many moles of acid that we've got. Now, it's a weak acid, but that's not all that important. I need to figure out how many moles of protons total I can titrate. So what I'm going to do is I'm going to take my molarity, the 0.1 mole per liter, and I'm going to multiply that by the volume of my sample in liters. Now I'm going to convert to liters here. Notice it's 40 milliliters in my sample, and I'm using 0.040 here. I divided by 1,000. The purpose of doing that was to convert to liters, because when you multiply molarity times the volume in liters, you get moles. So what this quick calculation has told me is that I've got 0.004 mole of HNO2. That's how much I've got to titrate. Now, in a similar vein then, I can compute how many moles of hydroxide ion I've got to use in this reaction. Same equation, molarity times volume in liters, right? So let's see, here our molarity was different. It was 0.2 for our titrant. And I'm going to multiply that 0.2. It looks like on this particular point I only added 5 mils, so that's 0.005 liters, right? So 0.2 mole per liter times 0.005, that's 5 milliliters. And I have only added 0.001 mole of my OH minus. Now that was, of course, added as the potassium hydroxide form as an aqueous solution. So you have equivalent moles of potassium, but this is a strong electrolyte and it dissociates completely, so that's how many moles of that I've got. Now before the reaction occurs, I'm going to say I have 0 moles of this one. Now so long as one of the reaction partners is a strong acid or base, we say that this reaction goes 100% to completion. It becomes a limiting reagent problem. You figure out which of the chemicals you're going to run out of first. And in this case, since it's a 1-to-1 stoichiometry, I'm going to run out of my hydroxide first. Once I react this 1 millimole, or 0.001 mole, I'm out of it and I can't react anymore. But I can consume 0.001 mole of this, and I have 0.003 mole left. Likewise, I'm going to make 0.001 mole of this. So you can see I'm just working my inventory, right? That's very consistent in all these problems. You work your inventory, and then you see what you've got once you're done, okay? So now I get to this point in this problem that's actually my favorite point, right? You got to look back at your inventory and decide what situation you've got. And here, what I'm noticing is that I've taken my acid, which was originally present in my beaker, and I've reacted it with OH to make the conjugate base. Now, I haven't reacted my acid completely. I still have 3/4 of what I started with left. But I've used 1/4 of that acid to make my NO2 minus, my conjugate base. And so right now, I've got a mixture of the acid and the base form in solution. This is a buffer. I've made a buffer inside this beaker in situ, what chemists might call it, okay? I've titrated some of my acid to make a buffer solution. And this is actually a really common way that buffer solutions are made. We talked about a buffer being a mixture of the acid and the base, the weak acid and base, and that's certainly true. But you don't have to buy both chemicals from a chemical supply house. You can actually just buy the acid and then come in and titrate it with some strong base, and you make the conjugate base in the solution. Now, whenever you have a buffer solution like this, you can always use our very friendly HH equation, our friendly Henderson Hasselbach, right? And what that tells you is that the pH of a solution is equal to the pKa plus the log of a ratio of concentrations. The base concentration or molarity divided by the acid's molarity. In the problem, we were told the pKa was 3.34, so I can plug that in directly. That's what the characteristic of this particular acid is. And then I just need to take the log of this ratio of concentrations, of molarities. Now, I suppose I'll spend a few seconds in being technically correct and convert my moles into molarities. So bear with me while I do that here. So what I'm going to do is compute my A minus form. That's my base concentration. Okay, that's analogous to the NO2 minus 1. So I've got 0.001 moles of it, and I have to divide that by a final volume in liters to get to my molarity. Now, I don't know what that final volume is right now. I guess I got to look. Let's see, I started with 40, and then I added 5, so it looks like 45 milliliters, which is 0.045 liters. Oops. So if I do the math, it looks like my A minus concentration, which is my base, is 0.0222 moles per liter. So I put that number here because that's my base. Now I also need my HA concentration. That's my acid concentration. And that is what? 0.003 mole divided by the same volume, 0.045 liters. So I should be 3 times bigger concentration. If I do that, which I'm confident I'm going to get here in a second. Indeed, that's the case. 0.06667 repeating molar. So the molar units cancel. And I have 0.0222 divided by 0.06667, about 0.33. So I take the log of 0.333, and my mathematics reduced down to adding 3.34 plus negative 0.4775. So if I add that number to 3.34, I get 2.86 for my pH. Alright, so it looks like then that we started to titrate some of our HNO2, and before we added any titrant the pH was 2.18, but now it's increased a little bit. It's gotten up to about 2.86, and that makes sense, doesn't it? Because I've added some strong base, I would expect the pH to drift up some. Now, how did we handle this situation? Again, the strategy is what's important for us, okay? It was real simple. I mean, we just made a logical statement of what the reaction was. We used our inventory-based approach to figure out how many moles of everything we had after the reaction occurred. We decided we had a buffer because we have a mix of a weak acid and its conjugate base. Because we have a buffer, we can use our Henderson Hasselbach. Can only use that equation when a buffer exists. That's important. But because we have a buffer, we can use it. We plugged and chugged, solved for our concentrations, figured out what the pH was. It was that simple. Alright, so that's how you handle that situation. Alright, let's move on to the next one. So we got B done. So in C, it looks like they want us to determine the volume of equivalence and half the volume of equivalence. And we want to know what is the pH at half the equivalence volume. Let's take a look at that. So first off, what do we mean by VEQ? Well, basically what that translates to is the equivalence volume. What that means is how much volume of titrant do you need to reach the equivalence point? In other words, how many milliliters will need to be drained from my burette to reach the equivalence point, okay? So let's see, how can we figure that out? Well, we know that the reaction is HNO2 plus OH minus makes water and NO2 minus. Now at the equivalence point, since it's a one-to-one stoichiometry, we need to have equivalent moles of both of these, right? Now in the previous problem, we decided that we found out how many moles of HNO2 were present by doing molarity times volume. And down here, it's a 0.1 mole per liter solution, and we had 40 milliliters, 0.040 liters. So I remember saying that we had 4 millimoles of this stuff, right? The acid. So basically, to end up with an amount of 0 after we account for the reaction, so our change would be that, we'd have 0 moles left. We need to basically have the same numbers for the OH. We need to start with 4 millimoles and use 4 millimoles and end up with 0, right? So that basically means to reach the equivalence point, I need to add 0.004 moles of the hydroxide. That's what I need, okay? So if I need 0.004 mole, and I know my molarity of my titrant is 0.2 from the problem, because I was told that in the problem, right? I can basically rearrange and solve for V, the volume necessary. So I do 0.004 and I divide by 0.2, and I get 0.020 liters, which is 20 milliliters. So my VEQ is going to occur right at 20 milliliters. So when I add 20 milliliters of my titrant, that's my equivalence point. That's where I'm going to be able to titrate all of my weak acid. Now, that's my VEQ. This problem also asked me to compute my half VEQ. That's pretty simple, because to figure out the half VEQ, that's the halfway point of the titration, you just have to take the equivalent volume and divide by 2. So that's going to occur at 10 milliliters, okay? Because the equivalence point's at 20, the halfway point then is at 10. Now in addition, part C has asked us to compute the pH at this halfway point. Let's take a look at that one for a second. What's the pH at the halfway point? Well, at 10 milliliters added, if we write our inventory, let's see what we get. So I'm saying that I'm at the halfway point, which is at 10 milliliters of titrant dispensed. I'm going to do my ICF inventory, as is typical. Now we've been saying all along that we have 0.004 moles of this stuff, right? Which is governed by a concentration of volume multiplying by one another. You get that. Now at this halfway point, what I'm interested in knowing is how many moles of this do I have, okay? So I'm going to do my calculation real fast. Mole of hydroxide is molarity times volume in liters. My molarity is 0.2, that's always specified and constant. And at this halfway point, we just decided that was going to be at 10 milliliters, which is 0.010 liters, okay? So if you do 0.01 times 0.2 on your calculator, you get 0.002. That's how many moles of OH that we've added at this halfway point at 10 milliliters, because that's the halfway point. That's what we've been talking about here. The problem becomes a limiting reagent problem, in which you use up 2 millimoles and don't have any of that stuff left, and you, in the process, consume 2 millimoles of this. So you do have a little bit of your weak acid left, and Start off with 0 of this, and you make 0.002 moles of the conjugate base. So look what we've got here. And remember, this is 1/2 the equivalence volume is what we're working this calculation for. We've got 0.002 moles of our acid left, and we've also made 0.002 moles of our base. Because we have a mixture of both the acid and the base simultaneously in solution, we've got a buffer. And whenever we have a buffer, we know that we can use that friendly Henderson Hasselbach, can't we? Okay, so we're going to add the pKa for the acid to the logarithm of the base-acid concentration ratio. Now let's eyeball this for a second. If we plug in the molarity for the base and the acid here and here, won't they be the same concentration? Because look, this one over here is the conjugate base, the deprotonated form, and then the one on the left, that's our acid. Acid, base. We have equivalent number of moles, and they're contained in exactly the same solution volume, so they're going to have exactly the same molarities. So what's the significance of that? Well, because these two have the same molarities, this ratio is going to reduce down to 1. Now, let me show you something. If you take the logarithm of 1 on your calculator, you get a big fat 0. So we are at a special point on our curve. We are at a special point where, because the concentration of the base and the acid are the same, the log of 1 becomes 0, and the whole equation reduces down to pH is equal to pKa. So at this halfway point of the titration, when you've added half the equivalence volume of titrant, when you're halfway home in terms of how much titrant you've added, you're at a very special point on the titration curve. And when you're talking about a weak acid with a strong base, such as we're talking about here, the pH at the halfway point is always the pKa. So the pH at this point is 3.34. That's actually a pretty useful way to estimate what the pKa of a weak acid is. If you carefully monitor the pH along the titration curve, and you figure out what the pH is at the halfway point, that pH should correspond to a pretty good estimate of the pKa. So that's what we're expecting at half the equivalence point, okay? All right, so now we need to move on to the next point, which is going to be our equivalence volume. So this is going to be D. Determine the pH at VEQ. Now earlier, when we were working through this problem, we decided that 20 milliliters of titrant added corresponded to the VEQ. So let's just, again, work through our inventory and see what characterizes this condition. So we start with the normal approach. We rewrite our equation. And we do the RICF business, right? All along we've been saying that we have 0.004 moles of this, but we need to figure out how many moles of OH we've added at this point. Again, moles is always molarity times volume. Now, the titrant molarity is 0.2, and if I'm at 20 milliliters added, I have 0.02 liters. Before the reaction starts, I don't have any of this, and I don't usually track water. So again, as long as one component's strong, which it is, proceed to the right completely. We don't have any of this left. Similarly, we use up all this. We don't have any of this left. And in fact, This is what defines my equivalence point, isn't it? At the equivalence point, the acid is completely consumed by the base and vice versa. This is the equivalence point. This is the meaning of it. The only thing, though, is in this titration, I've made 0.004 mole of the conjugate base, haven't I? Now, in the strong acid titration, that conjugate base was extremely, extremely weak and puny, like chloride ion or bromide ion, something like that. Something that would not affect the pH at all. But that's not the case here. Because I made an aqueous solution of my conjugate base, it can react with water to set up an equilibrium in which the conjugate base accepts a proton from water, and we also make hydroxide. This is a crucial and key reaction to be able to identify at the equivalence point of a titration of a weak acid with a strong base. It's the so-called hydrolysis reaction for this weak conjugate base. Now this is a weak base, but it's not as weak as chloride or bromide or something like that. It's much stronger and much better at accepting protons. And because of that, this type of reaction can take off. And we might make a small quantity of OH. And if we do, the pH will rise and be a little basic at the equivalence point. So maybe you can kind of see where we're going with this. I might be able to compute equilibrium concentrations of all these substances by using a Rice table. And in fact, that's going to be the approach that I want to take. Now, because it's a weak base, it does not proceed to 100%, so I have to draw my equilibrium arrows, and more importantly, I have to work the problem from an equilibrium perspective, meaning I have to write out the Rice table. Now when I'm doing that, I'm going to use units of molarity again, so I'm switching back to the concentration units here because it's an equilibrium. Alright, but we don't have to be scared by that. So let's think where to start. Where we're going to start with our initial amounts. Well, it seems like we had 0.004 moles of this conjugate base that was contained in, let's see, 20 plus 40. That's 60 milliliters of solution. Okay, so that 0.004 is contained in 60 milliliters of solution. So I can compute then a molarity, an initial molarity for my conjugate base, taking 0.004 and dividing by 0.06. And when I do that, I get 0.0667 mole per liter. And that's my initial concentration of this stuff before the reaction takes off. And of course I'll lose some as it proceeds to the right, and I make products. Start with 0 and 0, plus x, x and x. Products times products, divided by 0.0667 minus x. And this is going to have to equal one of my equilibrium constants, isn't it? But I have to ask myself, what equilibrium constant should I use? Should I use Ka, Kb? What do I need here, okay? Well, think about the reaction. If you write the reaction, you can always go back to it to help you. Here we have a weak base acting as a base, accepting a proton. So I need my Kb value for this ion. Now I look back to my problem, and I was told in the problem what the Ka was, but I don't have a Kb value, do I? So I need to remember that Ka times Kb is equal to Kw, and at room temperature, that's 1 times 10 to the minus 14th. So I can basically solve for Kb, and sometimes you need to do that in these problems. Writing everything out, Kb times Ka has to equal that number, and then I just do the math, right? So I do the 1e to the minus 14th. Let's see, where is it? So 1e to the minus 14th divided by 4.57 e to the minus 4. It looks like my KB value is 2.18 times 10 to the minus 11th. Okay. And then that has to equal this fraction. So now in this case, I'm pretty comfortable with making the simplifying assumption. I think that's probably going to work, okay? Because this is a tiny k, which means that this reaction is not going to go far to the right at all. X will be really, really small, so I'm going to pretend that that's not there. And then if I do, I could write what x squared is equal to 2.18 times 10 to the minus 11th times 0.0667. If I do the math on that, I get 2.18 e minus 11 times 0.0667. I get 1.45 times 10 to the minus 12 is equal to x squared. And now I have to take the square root of that. And I get 1.204 times 10 to the minus 1, 2, 3, 4, 5, 6 being equal to my x. Alright, so that's my x. Now if I go back to my table, I can understand what that means. And it looks like it's the concentration of hydroxide. So my hydroxide concentration should be 1.2 micromolar in this particular solution. So in fact, I haven't made much of it, but I can use this knowledge to help me calculate pOH as the negative log of that concentration. Alright, so I can compute my pOH then pretty easily. I can clear this negative, oops, I don't think I need second function, negative log of 1.2 e to the minus 6. And I get 5.92. That is not my pH, that's my pOH. But if I do 14 minus 5.92, I get 8.08 for my pH at this point. And you can see that indeed the pH is slightly basic at this point, a little over 8. And the reason why that is again this hydrolysis reaction of your weak base. At this point, at the equivalence point, don't lose sight of what we're doing, okay? At the equivalence point of the titration, all of your acid was converted into the conjugate base. All of the moles of the acid has now been converted there. That can act as a weak base by reacting with water to make hydroxide and the weak acid. But most importantly, you make the hydroxide. So if you take the initial moles of that base that you made, convert it to a molarity, plug it into your rice table, figure out how much hydroxide you make, compute pOH, and then pH. You can find the pH. But it's important to realize that for this type of titration, for a weak acid with a strong base, the pH is always a little bit basic. And the reason why is this hydrolysis reaction. That's the key chemical step. Okay, but your pH will always be a little bit basic. So this one's very different than the strong acid, strong base case that we learned about in before break. For strong acid, strong base, at the equivalence point, the pH was 7. But for weak acid, strong base, the pH is always a little bit basic, and we can see that here. Okay. Alright, so we've got one more point for this sample problem. The last point is point E. So this one had a pH of 8.08 here. It's a little bit basic at the equivalence. But we got one more. What is the pH after 40 mLs has been added, okay? I'm going to call this the excess titrant region, because now we've over-titrated. So we want to drain 40 mLs of titrant. So how are things different? How are things the same? Well, we always go back to our inventory, don't we? So we write the reaction to make water and the conjugate base. We go back to our ICF table to figure out how many moles of everything we've got. Because we haven't changed the sample volume or molarity, we still have 0.004 moles of this. But now we have changed the amount of OH we've added, because we added more, we added a higher volume. But remember, I can always do my molarity times my volume in liters, and that always gives me moles of my solute. And that's what I'm going to do here. So if I do 0.2 times 0.04, I get 0.008 moles of my hydroxide. Don't track the water. Before the reaction takes off, I'll say I don't have any of the conjugate base, okay? But now I can make an estimate of how things are at the final position. We assume the reaction proceeds to the right as far as possible. What that means is I'm going to consume all of my acid, aren't I? And I'm not going to have any of that left. But I can only consume this many moles of my hydroxide, which means I'm going to have 4 millimoles left over after the reaction is complete that cannot be neutralized. I'm also going to make 0.004 moles of this stuff, which is the conjugate base, okay? So after our back of the envelope initial guess of where we're at, we got to figure out what in the world controls the pH, all right? Now looking at this, it might be a little confusing, because we know that if you just put some hydroxide ion in solution, that matters for pH, because it affects the Kw expression. This NO2 minus also can act as a weak base and accept some protons, so that could also be important. But it turns out that this NO2 minus, because it's a weak base, it doesn't affect the amount of OH all that much, unless it's the only thing that's there that can change the pH, like we saw in that previous case. But I guess what I'm here to tell you right now is the amount of OH that we get from the over-titration, which is this excess, is almost always much more important. And to a first approximation, the molarity of OH in the solution can be found by taking the excess number of moles, the 0.004, and simply dividing by the total liters of solution. Now in this particular case, we added, what, 40 mLs? So we added 40 mLs of our titrant. We're not at 10 anymore. Now we added 40, and we had 40 to begin with, so that makes 80. So we're at a total volume of 80. So to a first approximation, my OH concentration in this solution can be found by 0.004 divided by 0.08, which is 0.05 mole per liter. Now, if that's my OH concentration to a good approximation, I can then take my negative log of 0.05, and that should be a pretty good estimate of my pOH. And that's what I'm going to do. That works out to be about 1.3. And then if I solve for my pH, by doing 14 minus 1.3, I get 12.7. So, to be honest with you, in the first approximation, if you're working in excess titrant regime, for your titration curve, the amount of excess moles of OH that you get from just over titrating is almost always much greater than any that you make through the hydrolysis reaction of this stuff. So this answer then would be a really good approximation of reality, and that's really all that we need to do for this point in the excess titrant region. So I'd say the pH is right around 12.7. That's what I'd expect for this particular point. All right, so we've now worked all the points on our curve. I wonder if we could just take a minute or two here to kind of rehash what we found and maybe even sketch out an example titration curve. Now remember, our titration curve is a plot of pH versus volume titrant added. That's usually in milliliters, okay? And here that titrant's a strong base, so this is a weak acid with a strong base titration. So pH versus volume of the titrant added. Let's see if we can make sense of all this, okay? Here's pH 7, so that's a neutral. Higher pHs, lower pHs, and I'm going to try my best here to be, I guess, as quantitative as possible. So we'll make this 6 and 5, 4, 3, 2, 1. Nine, 10, 11, 12, right? 9, 10, 11, 12, 13. Okay, great. Now on this axis, we've got our volume of our titrant added, and I think we went all the way up to 40 was our highest point. Let's try to divide that up, okay? Now our first point, determining before any titrant was added, that's at 0 titrant. We got 2.18, so we're right about here, right? Do we remember what controlled the pH there? Wasn't it just that we had this solution of the weak acid and it could donate some of its protons? We had to work the Rice table and figure out how many. We did that. We used the quadratic and figured out the pH was 2.18. But again, it's important to remember what controls the pH at each point. Then we added 5 milliliters of our KOH. So we'd actually be on our curve right about here. It's 5, right? So not very much titrant, and the pH jumped to 2.86. So that's a little bit of a change, but not a whole lot. I mean, we're still right about here, I guess. So if I'm connecting the dots, I'm going to have something like this. Okay. Get to that point right there. Now, do you remember what controlled the pH there after you drained a little bit of the KOH in? Didn't we have a buffer form? We used Henderson Hasselbach. Yeah, that was that buffering region. And I'll point that out in my plot here in a second. Moving on to C then. At C, we were at 1/2 VEQ. And we found the pH was 3.34. Did we remember what the half the VEQ was there? I think it was 10 milliliters, right? Yeah, 10 milliliters. So at 10 milliliters, we're at 3.34, so that's right about here. Okay, so we see that the pH is still kind of drifting upwards, right? And then the next point is at VEQ. pH was a little over 8, and that was at 20 milliliters. So let's see, 20 is here, pH 8 is right about here. So if I'm sketching the curve, what would it look like? It would actually remain pretty flat, almost until we're out here, and then it would take off like that. And that's my VEQ, my equivalence volume, the steepest point on my curve, okay? And then the last one was determining the pH after 40 mLs were added. Now it's out at 12.7, so that's way out here. Somewhere up here, right? So again, if I'm sketching out this curve, what it would look like, oops, would be something like this. Okay. So my weak acid with strong base curve, it looks similar to a strong acid, strong base case, but it's not quite as abrupt, okay? I guess that's what I want to highlight to y'all. These curves are a little bit more rounded in the weak acid case. It's not as abrupt a change. And then again, here at the beginning, we have this little inflection up into this so-called buffering region. Of our curve, that's in through here before the equivalence point, but after some of the titrant has been added. And that's because a buffer exists in solution in this region. So in this region of the curve, we can always use our HH equation to solve for pH. Okay? And right here at our equivalence point, what was important was the hydrolysis reaction of our weak base. That was the only thing that was important to set the pH there. And for this category of titration, it's always going to be a little bit basic at this point, at the equivalence point, because this reaction will take off a little bit. And then out in this region, this is our excess titrant. This is where we've just over-titrated, okay? You just have to figure out how much excess OH you've got from the over-titration and solve for pH using that. And then the only other point that I guess I've neglected is the first one. And that's before any of the titrant's been added. And there, what was important right there at zero titrant was the dissociation of the HA. So you use the Ka and the rice table, and that's how you solve for the pH there. All right. So hopefully this explanation has been useful. We'd want to be able to compute the pH along this type of titration curve, really for any weak acid-base titration. And you really work these the same way. You just use different numbers for concentrations, Ka, so on and so forth.